TAing for regression, but I am at the same time taking,
Y no vamos a
advanced
tener que andar como locos.
which is like a little, it's like 80% GLMs, and then now in the last part, we're doing Bayesian. So it's good that like, while like doing all of this more advanced stuff, I am at the same time remembering everything on like Russian one. Cause this is kind of like the basics, right, for everything, so it's kind of good.
But
Yeah.
this is the one course where you do have students to come to look for you, you know.
Yes, yes,
It's
it's the
not like-
methods are the only one where you actually have people on office hours every
I
week.
know.
It's like usually in like substantive course, people just go like, or the assignments or the exams. Yeah, they come.
Talvez tenha.
Yeah, they come. They're good. Yeah, I know, guys, we're very happy with them. Yes.
It's weird how we never. You know how we feeling and like, I don't know, it's not natural. I guess, but I can find that, yeah,
Yeah,
it can be rewarding to know sometimes.
yeah, I really like working with him too. He's very organized.
Wow, that's good. Yeah, it's teaching methods, so you have.
Aí faz quadradão assim, tipo. Ah, não, ela me perguntou como que queria que fizesse. Acho que assim fica melhor para semana parte.
Yeah.
I went for a run yesterday. Cause the thing is that like, I really wanted to like exercise this semester. So I kind of like, I put myself into like a coercion method. Because I subscribed for the Holy House. And I like registered for the Holy House.
Acho que valeu a pena.
April 20. But I'm not gonna do the 21 kilometers, just the 10. Okay. 10 kilometers. Yeah, so, but even so, like 10 kilometers is a lot. So I was like, well, if I don't train, I will run. I used to run a lot. Yeah, I used to run a lot. During the pandemics, I was going for the 21. So
Você tem
I.
pessoas que levam em conta.
Yeah, I was that I stopped running. The things are like, you stop.
Você
It's
leva algumas
like
paixõezinhas. Eu
almost
nunca
as
trabalhei
like
com isso,
starting.
então não sei se isso tá
Yeah.
embedded assim, alguma coisa. Pode ser uma coisa legal.
Oh, yeah.
Last year, second time, because I stopped maybe. It was so much more. It was
Yeah, no, I got
20 hours, that's slower.
all my life.
Yeah, so basically I'm like trying to run like at least once a week, or like if I can practice. Because I mean, I don't want to be fast, like I'm only like, I just want to finish the 10K without having a limiting, because I usually have a lot of pain. So my goal is to finish.
When I started running,
I would prefer statistical.
I started doing some.
I don't think. Statistical. That's not last. And then one.
Everything.
Mhm. Yeah, I think I went to
So it hurts?
yeah, and it's more like just because of the impact.
Talvez
You
faça
know,
uma coisa
so what I did back then was when I was doing some like strength exercise for the like for this muscles here, and it was working.
Depois só
Yeah.
batendo. A gente-
It's super stiff when
Yeah, because the impact is there. Still, it's going. Yeah. So yesterday I ran 8 kilometers.
It's better to be
So-
mixed up one. Yeah.
So I'm a bit sore, but I mean, not a lot, not like I'm dying and I'm just good.
I'll have you know that the data set I am currently working on is going to be used for regression discontinuity with multiple cutoffs.
Wow.
How many discontinuities? I think, so we're looking at GPA and attendance primarily, I think. So those are the two main ones, but I think are. We'll see. It's getting the actual outcome data is a struggle. With management performance hub, which is like Indiana's main database.
So you're not running an experiment in this days?
No, it's a observational study. Yeah,
This is for you?
yeah, it's kind of a weird one. So you guys are Corey Gibbs and Abigail Wozniak. We've been going around the state collecting like information on the certificate program that has these cutoffs. So we've had to go to like individual schools in the state over and over again and try and get their
I was trying to.
clean it, which is what I'm in the process of doing.
Oh, okay, okay.
Sí, gracias por mandar.
You have cases of.
Not terribly, I don't think it shows up as much in the setting, particularly for the RCT.
Pero ha sido.
To make sure you have enough power.
Yeah, exactly. Trying to think if any of the other, the quasi studies we picked up are nature.
Me refiero a que la calidad, ¿no? Pero vea que hay dos
Thing where it's like
jueves y viernes, pero es jueves
diff
y
and def
viernes.
with view treated or like a.
Yo no voy a poder hacer con todo me patrocinar a este y me lo pusieron cuando vine a ver cuando lo habían puesto empecé el jueves. Bueno, ahí nos expulsaron. No sé si va a estar Mayra. Sí, de Natal no va a ir, que yo tenemos otro. El sábado yo solo voy a poder, ojalá, salir el viernes en la tarde para llegar.
All right, so welcome back, everyone. So let's get started with the second session. Floor is yours.
Okay, so thank you so much for coming to the second part. So I think the idea here, we have like some simulations that I think would be nice to just like show you like if you actually are running or using the data, what you'll get depending on how you're constructing your estimator. So this is why I ask you to bring the laptops so we can like do together these kind of things. So, and I think like for the second part, we probably have more than enough time. Just to go back to the slides, I think it would be nice to talk a little bit about the design-based setting and how their solutions are not like something that gain that much relative to what we have been doing so far in the model-based. And then you can also go back like to questions. So I think there was a question on synthetic controls. You can talk more about that. So just to start, I think I have like this codes that I wrote, so no one will have like to start like coding like crazy here. It's just like following the scripts that I already made. So if you can just enter this site, maybe the easiest way is just like to look at my website and then add this field treated at the end. So you'll find a hidden page in my in my website that will lead you to there. And then you can decide whether you want to code with RS data. As I mentioned, I'm already old, so I didn't learn R. I'm still doing Stata, so you have a little bit more codes over there, but I mean, everything you need to do for now will be here. that. So if you got like, depending on the what we're doing, so I'm doing Stata, but I mean, you have like the same code in R that you have there. So what's the idea in this code? So here you decide what is the data set that you generate. So you go over like some different data sets that you might encounter in your life with different characteristics. And we see like how different methods will perform depending on the characteristics of the data. So we have like a definitive, okay. This one? Did anyone got access to that? Yep.
You can just search for.
No. Can you
Just the last.
This is filtered,
just zoom in, just
maybe. Yeah.
Yeah, okay. Oh, okay.
Four files.
If you're doing Stata, yes. Did it work? Yep. So what this first do file or R script is doing, we just like generate a data set. It will be like a setting where you have a diff in diff, you have 100 units, 20 periods, but you are in the setting where only unit 1 is actually receiving treatment. And then we have like 3 different data sets that you can generate. One in which you have the error term, and the error term is IID across everyone. So we see how this means. Then we relax this assumption and say, okay, now we have that the error has a serial correlation, but still it's IID across observations. So you are in that setting of Cohen-Tabor that you're just, if you want, you could extrapolate information from the treated, from the controls to the treated. And then you have like a third data set where you have heteroscedasticity. So we'll have another variable that will be like the sample size or the population size of each unit. And then the variance will be inversely proportional to this variable, to the population size. So if I put here and say the treated unit is actually smaller than the control units, we will be in the situation where you should expect to have over-reduction. So if you just run that to generate this data set with these characteristics, and it's nice here that I didn't put the seed, so everyone will run and will receive a different data set. But the nice characteristics, if you think about this multiverse, is that you're generating data from a DGP that there is no treatment effect. So the null hypothesis, if you're testing that the tau is equal to 0, this is actually true, this is correct. But of course, everyone will receive a different data set. So maybe you end up like rejecting the null or not rejecting the null, depending on the type of inference method that you are using. So we can just like run this one. Let's see if it works fine for all of you. Should be something like that. Where of course, if you're actually running the data, you would observe U and like all of those components. You will see like the units, the period, whether it's pulse or not, whether it's treated or not, and the outcome. And then we can go to the second do file or our script, which will see, okay, now let's do different inference methods. And then the first one is actually what you should expect people will do if they are just like doing whatever people are doing when they run diff and diff. They will probably have written or seen someone who have read and cited, oh, when they're doing a diff and diff, you need to cluster at the unit level, because this is what Bertrand, Duflo, and Mulaney did. And then you can just see what happens if you do that. And then you can check whether you reject the null or not. So I bet most of you got stars, right? Anyone got significant results?
Data set 2.
The one, data set 1. Yeah, so. No, we'll go one by one. Yeah. No, let's start with data set 1. So we run data set 1 and then we'll go back, yeah. Yes, thank you for checking on that. Let's go to the difficult case first. And then what's nice, if you go here to the first part, the idea is that, okay, everyone here like receives one realization. Imagine that you had like this diff in diff that you see, whoa, that's a good idea to run. You run that, but you are in a different multiverse where each one received a different realization of this data set. And then if you go here, we can just put what's your point estimate and what was your p-value when you use cluster robust standard error. So here this should be in mine. This should be minus 0.46.
There's a summary of p-values at the end, so that's what you want us to look at.
Yes, exactly. But you can do like point by point, that will be fine. Yeah, we can like put everything there. But I think the nice thing is that imagine that you are in a situation where you shouldn't expect to find stars. So everyone should have been said that, okay, we've had this diff idea, so we run that. It doesn't have an effect, so you shouldn't find significant effect, but you find lots of stars from there. So I got a p-value that is 0.000. So I should be naively happy that, look, I have something here, a report, I have significant results. Of course, what you'll see that probably everyone in this room also got a p-value that is very small, when no one should find something like that, or only 5% of the people in this room should actually find a p-value smaller than 5%. So did anyone not get significant results? No, right? Yes. 0.06. Wow, so it's not significant at 5? Oh, unlucky. Yeah. Well, this could happen. This is why you. 0.6? And what's your point estimate? 0.27. So you are running the cluster robust standard errors. Yeah, well, that's unexpected. But at the end, you collect the data and see, okay, you have for sure many more people than 5% of you that are getting results. And then, so we can run heteroscedasticity robust standard errors. And now I got a p-value of 0.12. Now I'm not rejecting the null anymore. And what's the heteroscedasticity robust standard error is doing here that is different from the cluster robust? Essentially, it's treating each of the time periods, and you have 10 post time periods, as kind of a separate event, assuming that the error term between time periods are independent. And this is actually true in this data set, because we're assuming that the error term CID, you don't have serial correlation. So in this case, I got like 0.12. I bet like most of you probably should get something that is not significant. And this is because these standard errors should be working a little bit better. So the first one, we're actually underestimating by a lot the variance estimator, because it was saying, look, I want an inference method that is robust, that allows for serial correlation and is heteroscedasticity robust. So at the end, it tries to estimate the variance, take into account the possibility of serial correlation, and also that treated and controls might have different distributions. So at the end, it does what we are doing in that first example that I mentioned. It's mainly estimating the variance of this first component that is looking for the difference post versus pre of the treated, estimating the variance of this error as 0. And is underestimating that a lot. The second one, which is funny, that we're doing something that is less sophisticated or not allowing for serial correlation, but in this setting where you don't have serial correlation, it will get you something that is more, that is closer to the real one. Because it's essentially assuming that each treated observation are independent events. So it's not like you have only one treated anymore. It's like you have 10 different treated observations and using all of these 10 treated observations to estimate the distribution of the treated. So in this case, it's actually doing a better job in terms of computing like the variance. But of course, it's doing a good job here because we don't have serial correlation. So this is actually an assumption that we're making that is actually true in this data set. In this final code here that will use like Conley Tabor, I mean, you can like go into details afterwards if you want, but essentially what you'll do will be to compute like this permutation. It will estimate like that different in errors and residuals between the post period and the pre-period, and then run like many permutations where you change like what is the W hat that you are putting as a treated, and then computing the number of times that you are greater than your treatment effect that you estimate. So if you run this guy, to take a little bit of while, but again, it will give you a p-value for me 0.23. So okay, that's really precise estimator that you had before using cluster robust standard errors that got, wow, I have like many stars. We just have seen that if you do heteroscedasticity robust standard errors, we lose all of our stars. If you go to Conley Tabor, we also lose the stars that you have. And of course, like this one will be the most correct one. So yeah, it has like the Ferman Pinto. We won't use it now because now we don't have heteroscedasticity. So if you just go to the end, you can print out the summary. I forgot that I shouldn't have that here. So in my case, I have that the point estimate is minus 0.46. Look out that this is not in the order that I'm asking you in the form. So we should put like the second number. So when you go to cluster robust standard error here, this is 0.00. Then you do heteroscedasticity robust. Again, recall that it's not in the same order. I changed one, but I didn't change the other. So now I'm sad I don't have stars anymore. And then use Conley Tabor again. I don't have stars anymore. And then submit. So once everyone have done that, I can go get a response and see what happened in this case. What should you expect? So again, we don't have an effect, so the null hypothesis is true. So if you have a method that is actually working well, you should expect that only 5% of you will get like significant results. But perhaps the inference method is not doing so well. So at the end, you have over-rejection, which means even though we shouldn't expect many people to get significant results, we get like way more than 5% getting that. So let me see if you started to compute that. No, I have the mouse here. So you can go here. Set one. So make it set one. Okay. You can see some patterns emerging here. Oh, I think this one switched, right? If you can confirm, the robust should be 0.488, and the cluster robust should be 0. Is it correct? I will change that manually here. So this one, no. Should be 0.488. This one should be 0. And this one as well is the flip. So this should be 0.36. Plus robust is 0. Is that correct? The one who put these numbers? This one should be 0.207. This one should be 0. So you see the pattern that is emerging here. So if you just do cluster robust, almost everyone got a 0 p-value, which is expected. You are severely underestimating the variance of the estimator that we're doing. If you go to the robust, it got a little bit better. So it's what you expect. Some people will get lucky, quote unquote, and got something close to significant, but okay, this is what you expect. So if you just copy this thing here and put in Stata, let's see, clear, data editor, and you go there to analyze the data. So let's see, I put here cluster robust variance estimator. So this is the data set that you just generated. If the inference method were working correctly, you should expect that the p-value has a uniform distribution. So you should expect all of the data points to be over the 45-degree line. But what we are seeing is that almost every one of you, or every one of you, is actually getting 0 p-values, which means everyone is getting stars that you shouldn't be getting. When you go to the robust, then you get something a little bit better. So you have some people getting something close to 0.5, and then a more closer distribution to the 45-degree line. And if you use Collin-Tabor, oh, that's weird. It shouldn't be that. Let's see. Ah, CT minúsculo. Again, we are closer to the 45-degree line. This is, of course, we have like, I think 14 or 15 points. We can do the same thing, but actually running like many simulations, and it takes a while, so I already did that. So if you run cluster robust variance estimator, and if you did like 5,000 times of replications like that, then this is what you get. Like 80% of the time, or 83% of the time, we are receiving a data set where we reject the null at 5%, which is not what you should expect. You should expect that 5% of the time we will reject at 5% if the method is working well. If you run the robust, works pretty well, decently, so we reject 7.5%. The point here is that you only have 10 treated, so 10 is not that large so that asymptotic approximation is like really perfect, but still it works like decently well. And if you go to Collin-Tabor, here is with capitals. Now it gets like a rejection rate of 5.2. We have the distribution of the p-values is exactly the distribution of an uniform. So the 5.2 is just that, okay, you have some sampling variation because I have 5,000 replications. If we used more replications, it will be like even closer to 5%. Okay, so any questions on that? So at the end, what's the idea is it really shows that we're in a situation where if you just ignore the fact that you have one treated and you're just using like cluster robust standard errors at the unit level, but have only one treated unit, at the end you massively underestimate your variance. Many of you or most of you will get significant results that you shouldn't receive.
So just to do a quick recap, so this is the first example that you started this morning, right? So I have one,
Exactly.
I have clusters and then IID observations inside the clusters.
Mm,
How is it-
no, the DGP will say that you have one treated observation, one treated unit. This treated unit you observe over 10 periods, and half of these periods you have treated, half of these periods you have controls. But Colin-Tabor works really well because the distribution across treated and controls is exactly the same. So by design. So when I do this permutation where I use information from the controls to know about the distribution of the treated, it works perfectly well.
The cluster robust because the time periods are independent.
Exactly. So the robust is working well because it assumes that the time periods are independent. So at the end, it sees each of the treated units as an independent realization, and this is actually true. So when you just run the robust, it doesn't get there at 5% because we don't have like really many treated and control periods, but still it does a decent job. But this will not be the case now that you use data set number 2. So you just run this one. And then we can again run all of the inference methods. If you run cluster robust, it's the same thing. You continue to have only one treated unit, so it will continue to look at this unit cluster as estimating this variance between treated post-period versus pre-treated as a 0. So it will underestimate a lot the treatment period, the variance of the estimator. If you run the robust, I'm not rejecting, but I bet many of you would actually reject. And if you run Colin-Tabor, it should work really well because here Colin-Tabor is actually still valid. Recall that Colin-Tabor does not put any restriction on the serial correlation because it will collapse the information of the pre minus post, the post minus pre periods, and then like this cross-section comparison that it's doing takes into account the serial correlation, and you have the assumption that the errors have the same distribution across units. So it should work really well. So again, so if you just get it here, then you post your results in the second form.
I cannot, don't have access to form 2 right now.
Oh, really?
Change it to become.
Yes, is it? Let me see. Results from data set 2. Is it here? Where editor view, responder view. Anyone with the link? Okay, so now it should work. Do that. Data set 3. 1. Okay.
So for the code, the only thing that we're going to change is the data set object in the beginning.
I'm sorry.
Code is the data set.
Exactly. You should put 2 here. Then, okay. Let me see. Remember just that this is cluster robust, it's not in the order. So the cluster robust is 0, heteroscedastic robust 0.115, Colin Tabor 0.582. We're getting some responses here. That's funny. Not many people got rejections under the robust. So this one got really lucky. So got 1.5 of an estimate. You see the Tabor like still does not reject at 5%, but is actually close because we're actually getting one of the most extreme of the distributions that we expect, given like this setting where you have only one treated group. So the cluster robust will say, wow, we're really getting something significant here because it thinks that the standard error is like very small. The peer robust as well, but the Tabor would be a little bit more cautious about that. And the robust, yes, we have one 0.058. I should expect to have at least one or two being significant. So let's go straight to the results using the simulations with the 5,000 simulations. Here, if you use cluster robust variance estimator, it's the same thing as you had before. It's really underestimating, saying that the variance in this cluster that is the treated one is 0. So everything, like every point that you find, if you got a point estimate of 0.1, 0.2, it's to say, wow, that's really significant because the variance, our estimator is really precise. Of course, it's completely wrong because it is estimating like the variance, which should be like a positive number as a 0. If you go to the robust one, it gets now way worse than we had before, because before the heteroscedasticity robust, we're assuming that the time periods, the different time periods are independent observations. So at the end, it will say, well, this is actually true. So at the end, I have like 10 observations that are treated, 10 as a control, and I can deal with that. I mean, not perfectly, but quite well. But now that the data set has some serial correlation, this heteroscedasticity robust will start to over-reject. And what's the main intuition here? It's because since you have serial correlation, sometimes you'll find like a positive effect because you have like the first period of treatment, you have some change in the trajectories of the treated versus the control. But if you have a serial correlation, it's very likely that the second time period will also have a gap, and the third one, and the fourth, and so on. Because if you have like a positive shock in your error in the first period, you expect to have that as well in the second period, and so on. And if you're just looking at heteroscedasticity robust standard errors, it does not allow for that. It will see if I had like one positive shock in the first period of time that are treated, and then if in the second one is also positive, and the third one, and so on, it will say, well, it must be that there is a treatment effect here, because it's not taking into account that these events or these treatment assignments are not independent events. And this is what's showing here. So at the end, you reject 26% of the time. Even if I increase the number of pre-treatment periods and post-treatment periods, it will continue to over-reject. So it's not a matter of having few observations. It's a matter that I'm assuming, or using the inference method that is assuming that I have independence between the time periods, but at the end I have some dependence. So it will underestimate that. if the dependency is, yeah. Yes, you could under reject, because what would happen in this case is that I have like one positive shock, and then in the second period of treatment, you have a negative shock. So these things will actually will cancel out each other, and your standard error will not take into account that. It will underestimate the variance of the average treatment effect. So it will go to the other way. And again, if you do Colin and Tabor, it works perfectly well. I mean, it's not magic. I'm designing a data set that this thing will work really well. And let's just go to the third data set. So what's different in this data set is now we have, let's see if I can find it here. Now we have this variable M that is like the number of, or the population size of each of the units. And when I generate the error, I'm scaling the variance of the unit by this term here. So if M is higher, it means that the variance of this unit will actually be smaller, and vice versa. So, and also I'm generating the treated unit as having 300 population, while the control units will be between 100 and 5,000. So you expect the treated unit actually to have a smaller population size relative to the controls. Another way to see that, you expect the variance of the treated unit to be higher than the variance of the controls. So if you just go and try to do the same analysis again, you should expect always something similar when you run, let's see, when you run cluster robust, always have like these t statistics of 25. By now, you already know that you shouldn't be so happy if you find something like that. The heteroschedasticity robust, you see, now I got lucky, I got like p-value of 0.01. Again, it's just because my heteroschedasticity robust standard error is not taking into account serial correlation. And if I run Colin and Tabor, I got 0.0118. Remember, I shouldn't find a significant effect here. I bet a bunch of you got significant effects. What's going on? The main point is that the treated unit has a larger variance relative to the controls, and trying to extrapolate the distribution of the treated unit, of the error of the treated unit, using my controls, so I'm actually underestimating this dispersion. So at the end, I should expect to find more significant effects than I should. And actually, this is the funny story that I was going to tell. If you do the flip side, this also works the other way around. If it happened that my treated unit had more observations than the controls, at the end, the controls will recover a distribution that is with a higher variance relative to what it should be of the treated unit. And at the end, I would end up under rejecting. And this is actually this solution, or this first noticing that, and then the solution that I proposed later on in this Ferman and Pinto paper, is actually how I started to do econometrics, because I had a paper that used a diff-in-diff setting where the treated unit was Rio de Janeiro in Brazil. The control units were like the other states that you have in Brazil. And Rio is a relatively larger state in terms of population. And I sent this paper to a journal. It got a revise and resubmit. And one of the things that I was doing in that paper was to do a kind of a permutation test, because I had only one treated state. But I was like kind of taking into account in some rudimentary way that Rio was bigger relative to the controls. And then I got my results there. But then one of the referees told me, yeah, I think it's nice the way we are doing inference, but it seems like you're just doing Colin and Tabor. So you don't need to reinvent that. You can just like go there, use Colin and Tabor, and then write our paper. What do you think was the problem? Huh? Not a, well, the difference variance is the problem, but the main problem for me in that case, recall, I submitted the paper, I got like this diff in diff, I got some significant results, I sent the paper, and then the referee told me to do Colin Tabor. What happened with my stars? Since Rio is very big, it disappeared. So all my trajectory as an econometrician started because I wanted to get my stars back. So what I realized back then, well, there was a reason why Colin Tabor is not giving me the stars that I wanted, because Rio is actually a bigger state. So when I start like doing this permutation, I'm using smaller states that have much bigger variance as the, and then I was recovering a distribution that has a much bigger variance. And then I should expect to be under rejecting. If it was the opposite, if Rio was were a large state, then I will run Colin Tabor. I got like even smaller p-values. I will be super happy. I will resubmit my paper and will never become an econometrician. So this is funny how things work. But yes, this is what happened. So what I did, so I had like a rudimentary version, like in the revision that I submitted. By the way, the paper got rejected after the resubmission, but it already served its purpose. Actually, it got me into the PhD and then led me to do metrics. What we'll do in this case is just that we will look at the residuals of the controls. So this is what I'm doing here. And then I'm regressing the residual square on a constant and this variable key, which is 1 over the population size. So what I'm doing here is exactly, I'm postulating that the variance of a unit J depends in a linear way that is a constant plus another constant divided by the number of observations. And then I estimating that into the data. And then with what this estimation shows us is exactly that we should expect units that have higher population sizes to have smaller variances. And then we can use that to predict what will be the variance of each observation given the population size that it has. And then when you do the permutation that Colin Tabor will be doing, we actually take that into account. So if you have my treated state is relatively small, then I have like the error term of a control state that is very big. What it's doing here is that I know that this control state has a smaller variance. So if the residual that I observe for him is say 0.2, I know that the variance should be higher. So when I'm using that to recover the distribution of my treated, I will actually inflate the residual that I find for him. In the same fashion, if I have a control state that is actually smaller than my treated state, then I know that this control state has a lower variance. So what I will do, I will shrink the residual that I found for him. So at the end, I will be able to recover a distribution that has the same variance as my treated unit. And then again, if I run that here, I already defined that. So you have to run from here. No, I have to run everything so it runs. Oh my God, what's going on? Have to run everything. So data set 3, inference methods. So it will run Colin Tabor, it will run Ferman Pinto. And again, you see, now I would reject with cluster robust standard errors. That's the standard one, the one that underestimates the most the variance of my estimator. I reject with robust standard errors, and it's a pretty bad reject because I got a large point estimate. So, but again, I will expect to be over rejecting here because I'm not taking into account zero correlation. But the new part is that I'm rejecting with Colin Tabor, And this is happening because my treated unit has actually a higher variance relative to the controls, but I'm not rejecting with Ferman Pinto, because Ferman Pinto is actually taking into account that my treated unit is has a higher variance relative to the controls. So again, we can put in the forms, but I think it's easier just to go over the part where I analyze using the 5,000 simulations. So again, if you just run cluster robust, is the same thing. I'm rejecting 91%. If I run the robust, I reject at 28. Is the same thing. Here I'm rejecting because I'm not taking into account that I have a serial correlation. But the novel part relative to the previous data sets that we run is that if I run Cohen and Tabor, which ignores the fact that my treated unit is smaller than the control ones, then I also over rejecting. So I have like 26% of the times I will be rejecting the null, whereas I should be expecting, if the model or the inference method was working well, to reject only at 5%. And again, if I run Ferman and Pinto, it will get much better. So it'll be much closer to have a distribution of p-values that is closer to 5%. Still, I get 7% here, and this happens because I have a finite number of control units to estimate this heteroscedasticity. So at the end, I don't have exactly 5%, which will be like the method is valid for this given number of control units. But if I started to have more and more control units, then this rejection rate with Ferman and Pinto will actually converge to 5%. Again, given that we are in a data set in which the heteroscedasticity is only coming from this difference in population sizes. So do you have any questions on that?
I have this question, thinking more about how this method compares when you have a different design and estimated by the Galway and Santana.
Mm.
I understand, and I maybe this is correct, that the control unit is the unit that is eventually treated. So, you know, you have a treated unit and a control, right?
Mhm.
So don't rely on like purely control measures that are controlled
Yes.
over time. So basically, here you are leveraging the information from the units that are never treated. As
Yes.
well, in addition to the own unit that was there, so pre-treatment, right? And so, I mean, maybe
Yeah,
some
no, that-
question, but can you talk a little bit?
Sure,
about
sure.
this?
Yeah, that,
like,
that-
I like it.
sure. Yes. Mhm. Yeah, no, that's an excellent point, that excellent question. So I have another paper with Luis Alvarez, who is also a co-author on the survey, where we extend these ideas to the settings where you have variation in treatment timing. And one thing that is interesting is that most of these methods, they are mainly 2-by-2 comparisons, where you have like comparison between one period post versus pre versus another group, which might be like they eventually treated. Then you can choose like which groups that you are choosing. And what you can show is that you can extend that idea to these kind of settings. But of course, you need to have like many controls or controls that you are using in these 2-by-2 comparisons. So if you are in a setting where the yet to be treated is not very large, then this will be a problem to use this approach. But if you use like all of the controls, maybe this approach will be better. But of course, you have to balance that with what is the assumption, identification assumption that you are willing to assume, whether you have parallel trends only if you consider the yet to be treated, or if you are assuming that you can have the parallel trends assumption with the full controls, including the never treated as well. So if you are confident that parallel trends is valid using the never treated, then you can do that. This way you have just a little adjustment. The only method that we do not cover in that paper is the one of Pedro's Santana. I don't remember if it's the Callaway Santana or the other, that he does like the doubly robust estimator, that you estimate a propensity score. And I think for these settings where you have a fixed number or a small number of treated, it will probably not be a good idea to estimate a propensity score because you have only few treated to estimate the probability of being treated. So in that paper of ours, we don't extend to this method, but most of the other ones will be just a matter of which kind of 2x2 comparisons that we're doing. And then the idea is that you do this kind of Cohen-Tabor or Ferman Pinto on each of the 2x2 comparisons, and then you aggregate that, and that works fine. Yes. So other questions? Yes, you had the question before, but if you want to, that one or a new one?
Basically, the thing in Kellogg and Santana is that there's no straightforward way to covariate. So basically, you're saying that there's like a trade-off between like, is there like an efficiency or bias thing related to the value of the law?
Yeah, so the way I see that is that with the Callaway and Santana, I mean, we want to include covariates in our regression because you think that parallel trends works only when you condition on that. So you can include that as regressors. And if you do that, it will work if it's actually the case that the conditional expectation of Y0 is actually a parallel trends plus linear in the covariates. So you're getting right the conditional expectation. Or you can try to do the propensity score. And the idea of Callaway Santana is that it's an estimator that will be valid if either one of those are working. The argument that I made was that if you're just including that as a control and you're right that the conditional expectation is linear on the covariates, everything that we're saying here will be valid because you have many control units, so you can estimate well this relationship between Y0 and the covariates. And then you just do like this extrapolation of the errors after partialing out the axis. But at the same time, the inverse probability weighting, which is like the second part in which Kellogg and Santana will be robust, will not work well here because you will not be able to estimate the propensity score well. So this is why it's not possible or maybe not advisable to use inverse probability weighting. And for the same reason, it's not valid or advisable to do Kellogg and Santana in this kind of settings, because one part in which it will be robust, which is, okay, I'm getting right the propensity score, this actually will not work well if you have few treated.
Treated to like
yes, that's an excellent question. Yes, no, that's an excellent question. Yep. Yeah, so that's an excellent question. And unfortunately, it's a question that I don't have a good answer because it doesn't work like that. So you have like this result from Bahador and Savage that will tell that it doesn't matter like the number of observations that you have. You can also find a distribution of the errors that will be like so mean to you that would reject at 100%. So there is always a distribution that can be like as bad that even if you had like 1,000 observations, I mean, it's still be bad. But some things that you could do will be, for example, I have another paper that I advocate that you should at least run some simulations and see that, okay, even if you have a very simple data set, a very simple DGP where the errors are normal, so everything should work like, well, do I get like massive over rejections? And if it doesn't pass, even for those simulations, I mean, you definitely should worry that your number of observations is not that large. What's the problem of that? Is that maybe your errors in your simulation that you are doing, they are more kind for you and are not detecting something, that your real data set that was generated by a data generating process created by God and not by you would actually have some relevant of a rejection, and that we wouldn't know. But my recommendation will be to, at the very least, run some simulations and see that in the simulations things work fine. If not, then you should go to another method. If it works fine, you still like think whether your data set could have some, whether your empirical application could have some characteristics in which your simulations are not capturing that could lead you to some higher difficulties in having this asymptotic theory being a good approximation. But yes, I think that will be my answer. But if you want like some rules of thumb that people use, like, okay, if you have like 30 observations, maybe that's good, but I think it's hard to tell. What is really important is like this main message that it doesn't matter like the total amount of observations that you have, because you could have like 1 million observations, but if only 3 are treated, you are screwed. You have to have many treated and many controls. And the other message that actually I got like many mails like that, people asking, oh, I should use like your method because I'm in a setting that I have only 0.1% of my of my sample is being treated. So please help me to use like the method that you're proposing. And then after some time, I realized that the guy had 100 observations. And then I have to say, well, if you want to cite my paper, I will be glad, but you don't need to use, to use the method that I'm proposing. And that's actually really, really common. So yeah, any other questions? So yeah, you had the question on synthetic controls, right? If you want to discuss a little bit on that.
It seems like it's holding apply micro sometimes if you use synthetic control when it's only one unit treated.
Mhm. Yes, no, that's an interesting point. Actually, it's the continuation of the story that I mentioned about how I started doing metrics. Because the first paper I wrote was like a Ferman and Pinto that, okay, we have a different diff and we want to do inference. So if you have a heuristic elasticity, things get problematic. And then when I started to present this paper, like the first question that I usually got, like in the second slide would be, oh, but you're looking at a case where you have different diff and only one treated. So why don't you use synthetic controls? And then I had to start and learn what synthetic controls are. And then I started to run a couple of papers on synthetic controls. So everything was very path dependent. I have written like a couple of papers related to that, especially trying to clarify what are the conditions in which the synthetic control method would relax the assumptions that you need to actually get an asymptotically unbiased estimator. And if you want like to really summarize that, if you go to diff and diff, you allow for confounders that are time invariant. So your treated can be different from the controls in a way that is fixed over time. So at the end, you're extrapolating from the controls what is happening after the treatment. And it allows you to have like unobserved confounders that are varying in time, but is the same for both treated and controls. Because again, the time fixed effects will take care of that, or when you do like the comparison in the post-treatment periods between treated and controls, you take care of these confounders. When you go to the synthetic controls, the way I like to see it is, okay, but what if you want to have the possibility of some confounders that are actually varying over time? And in particular, if you have some kind of confounders that are some shocks that are varying over time, but that can affect units very differently. So for example, if you have a shock that is like the oil price, but you think that the oil price, okay, is changing over time, is the same for everyone, but it will affect countries very differently depending on whether you're exporter or an importer, for example. So this is not something, if you think that this oil shock and how you're affected by a oil shock is something that is correlated with your treatment, the unit and time fixed effects will not take that into account. So what the synthetic control will do is to try to recover a weighted average of the control unit that is affected by these common shocks in the same way as the treated unit, and then use that as a control, because then you'll be comparing something that is comparable. So the main issue is, okay, if you are in the situation where you believe your confounders may be coming from this kind of factor structure, which is like these common shocks that may affect people differently. Under some situations, the synthetic controls are able to deal with that and give you an asymptotically unbiased result. And I have like a bunch of papers that I've written about that, and combined with the papers from Abadi. I mean, if you have like a long time series and you have a fit that is very good, then you are taking care about you are taking care of these confounders. Then I have another paper that shows that if the pretreatment fit is actually not perfect, then you are not actually taking care of the confounders, but you're better than what you have done that you would be doing with the diff in diff, because you are going into the direction of having a weighted average of the controls that is actually affected by these common shocks, more closely related to the treated, but are not going all the way, so we still have some bias. I have another paper when you have like many controls and many treated that sometimes relaxes and assumes that you are able to get this weighted average of the control units that actually are doing a good job in constructing your counterfractals. So then it really depends on what are the setting that you are doing. So it depends on what are the kind of assumptions that you are willing to make on the selection, and whether you are in a setting where the synthetic controls will do a good job for you. So for example, if you have 3 pre-treatment periods or 2 pre-treatment periods, then synthetic controls is probably not that good of an idea. While if you are assuming that the parallel trends of diff in diff is valid, you can still use diff in diff. And so this is the kind of trade-offs that you have to be thinking. I mean, diff in diff will have some advantages. I mean, it will not require a large number of pre-treatment periods. It's simpler. Doing inference is actually much simpler than doing inference in the synthetic controls. But again, maybe these assumptions of parallel trends is not something that will be attractive for you in your setting. So maybe it's worth like considering other alternatives. So I think this is not nutshell what is my view of this kind of trade-offs that you have between using diff in diff and synthetic controls. Okay.
Any other questions from the online participant? Questions? All right. Let's thank Bruno.
Thank you so much.